Okay, so moving on to today's topic. If you remember from Thursday last week, we talked about heat engines. So we're going to continue our discussion of devices that operate between thermal reservoirs, but we're now going to include heat pumps and refrigerators. And so we'll talk about the differences between heat pumps and refrigerators, but then also look at them and how they compare to heat engines and what the differences are there. And then we learned some additional tools for how to analyze these systems, how to use them to design effective heat pumps or refrigerators that will work best for the conditions under which we're operating. Because depending on your high and low temperature reservoir, there may be different parameters that you have to meet in order to have the most effective or efficient heat pump or refrigerator that you can. So new homework assignments due 1 week from today. Again, these I think in general are a little bit easier than some of the other problems that we've done, but keep on top of it. Don't wait till the last minute. Make sure you understand it. You know, I've had a few questions about, well, what, you know, I didn't do so well on the exam. What can I do? The best thing you can do is just from moving forward is figure out what it is you're still struggling with, what you had problems with on the exam, and then try to really embody and understand those concepts, because we're still using the same ideas, the same techniques to analyze steady flow engineering devices, analyzing systems. So if there's something fundamental that you're not understanding, come talk to me. We can work through it. We can try to make it a little bit easier for you to approach these problems and solve them on your own, because that's essentially what this class is about, is being able to independently analyze these engineering systems. So again, all real processes have to satisfy both the first and the second law of thermodynamics. So first law is conservation of energy. Second law is quality of energy, or the direction of energy. And we talked about how the second law actually helps us determine the theoretical limits of a process. So we can predict whether or not this process can actually occur using the second law. But we will learn ways that we can use the second law also to determine not only whether or not it will occur, but also the extent to which it will occur, what the theoretical efficiency limits are as we start using some of the Carnot approach, which we get into next lecture. So heat engines, we talked about how they are used to obtain a network output using heat. And that you have some high temperature heat source, which is where you receive some energy into your system, and part of that energy is converted to work, but not all. So a heat engine can never be 100% efficient. There has to be some low temperature sink to which we dump an excess amount of heat. So only a portion of the heat that we obtain from this high temperature source can actually be converted into usable work, which is not ideal, but it's better than nothing. So heat sometimes can be found from the environment, and it's essentially a source of free energy, although the process to convert it to work does require some elements that are not free from work input as well. A refrigerator is similar in that it operates between a warm environment and a cold environment, or a heat source and a heat sink. But in this case, we're using a network input to reverse the flow of heat. So ordinarily, heat would flow from the warm environment towards the cold environment. But if we want to reverse that, we have to use work in order to make the heat flow upstream, or uphill, if you will. So for a refrigerator, this cold environment is the inside of the refrigerator. So we have a desire to keep our food cold and to make that space colder than the ambient temperature. And so with a network input and using a thermodynamic cycle with steady flow engineering devices, we can do that and then deposit that heat to the environment outside. So as we look back at the very beginning of the semester, where there was that particular example with a refrigerator in a closed room, and we asked the question, okay, will the room get warmer or colder with the door open to the fridge? Okay, you can see again here how we're removing some amount of heat from that cold space, but we're depositing even more heat into the environment. So we can't just assume that it's going to make the entire room cold, because the room now has become the source and the sink, and it doesn't cool down. It actually continues to get hotter, and then the cycle will break down. So with a refrigerator, we usually have an evaporator, condenser, compressor, and an expansion valve, which is a constant enthalpy device. So heat is removed from the refrigerated space. So we call that Q sub L, and that temperature that we're desiring to maintain in the fridge is T sub L. And then QH is the amount of heat that's rejected to the kitchen environment at T sub H. So whatever the temperature is of the space, usually in the back of the refrigerator or the top of the refrigerator at T sub H. And then the work net in is just the amount of work that's required to operate the compressor. So with a heat engine, we had a pump and a turbine. So there was some network output, which was the work out of the turbine minus the work into the pump. But with a refrigerator, we use this expansion valve to accomplish a significant pressure drop without requiring any work input. So the only work input is to the compressor, which is used to pump or condense, and not condense, but to compress and pressurize this this refrigerant and then send it to the condenser. So with refrigerators and heat pumps, instead of calculating an efficiency, we calculate something called the coefficient of performance, which actually can be greater than 1, which is why we don't call it efficiency, because then it somehow makes it seem like we have a greater than 100% efficiency, or that we're getting work from somewhere that, or getting work from nothing. But we use the same principle, that it's the desired output over our required input. So our desired output actually is to remove heat from the refrigerated space. So Q sub L is the desired output, even though it's an input to our evaporator. We're desiring that Q sub L is removed from that space. And then we're required to put in some net work in order to make that happen. So we can also rewrite the coefficient of performance as Q sub L over QH minus QL if we substitute in the fact that the work net in performing an energy balance on this entire system is equal to QH minus QL. So those are our only two inputs, are Q sub L and work in, and then we have an output of QH, which is equal to Q sub L plus the work net in. So we have to remove heat from the system equal to the amount of heat we're removing from the refrigerated space plus the amount of work that we put into the system. Okay, so those two combine. So we're actually removing more heat from our refrigerator than just what we're removing from the refrigerated space. We also have to take into account the work that we put into the system and how it turns into heat in the condenser. So let's do an example. And again, these are fairly simplistic. The difficulty or the tricky part now is just making sure that we're analyzing our system using the correct equations, because it's slightly different for a refrigerator than it is for a heat pump or for a heat engine, because our work and our heat interactions are in different directions. So if we have a refrigerator maintained at 4 degrees Celsius by removing heat from it at a rate of 360 kilojoules per minute, the required power input to the refrigerator is 2 kilowatts. Determine A, the coefficient of performance, and B, the rate of heat rejection to the room. Okay, so we know Q sub L is 360 kilojoules per minute. We know the work net in is 2 kilowatts. And we know the temperature of the environment, although in this case, we don't actually need to use that for any of our calculations. So how do we calculate our coefficient of performance for this refrigerator? Okay, so solve for Q sub L. Solve for Q sub H. What is our desired outcome for a refrigerator? What does a fridge do? Gets colder. Okay, so is Q sub H what we're concerned about? Is that our desired output, is Q sub H? Or desired outcome? No, Q sub L is the desired outcome, right? So if you forget the equation for coefficient of performance, you think, okay, what is the whole point of this system? It's to remove Q sub L from the food compartment. So if we calculate our coefficient of performance, it's based on our desired outcome, which is removing Q sub L from the refrigerated space divided by the required input, which is this work net in. So Q sub L is 360 kilojoules per minute, and work net in is 2 kilowatts. Are those equivalent units? Yeah, we need to convert this to seconds, right? So a kilowatt is a kilojoule per second. So we need to make sure that this is in terms of seconds. So 1 minute is equal to 60 seconds. We have to divide that through by 60. So we get 360 divided by 60 over 2, which is 6 over 2, gives us a coefficient of performance of 3. Okay, so again, the COP values can be greater than 1. It's not like efficiency because we're not converting heat to work. We're converting work to heat. So we can do that. We obtain some heat from the environment plus the amount of heat work we put into the system. Okay, so work net in is 2 kilowatts. We want to find Q dot H. So what's the relationship between QH, QL, and work in? Okay, so work in is equal to Q dot H minus Q dot L, which is equal to Q dot H. Oh, we're solving for Q dot H, that's why. So we reverse that. Q dot H is equal to work dot in plus Q dot L. So those two add together, work in and QL, to give us a larger value for QH. So we can either convert the work in to kilojoules per minute or convert QL into kilowatts. Either one is fine. So 2 kilowatts plus Q dot L is 6 kilowatts. That gives us 8 kilowatts, which is also equal to 480 kilojoules per minute. So depending on which form you want it in. Okay, so again, very easy equations. The confusion comes in when we start looking at heat engines, refrigerators, and heat pumps and dealing with them differently. So coefficient of performance versus efficiency versus work in and work out. We have to make sure we understand the systems. Okay, so a heat pump is used to supply heat to a warm space, usually the indoors, by extracting heat from a cooler space, which is the outdoors. So did you know that your heat pump operates by taking some latent heat from the outside? So on a day where it's 30 degrees, there's some heat in the air, and by the magic of thermodynamic cycles, it's putting heat into your house that's greater than the amount of work that it pulls in from the electricity. Okay, because you could use a resistance heater, right? You could plug it into the wall and heat your house just by having electricity run through a wire and add heat to the room. So 100% of that work coming in can be converted to heat, and that's some amount of heat that's added to your room. But with a heat pump, we can also take some heat from the outside. I know it doesn't seem like there's any heat in the outside, but we can take heat from the outside and add that to the work that we put in to add an even greater amount of heat to our house or to our room. Thermodynamics, awesome, right? Okay, but still we require some network input. We can't just transfer heat from the outside to the inside without this cycle happening. So by condensing and expanding a refrigerant, we're able to transfer heat in that way. And it operates in a very similar manner to a refrigerator, but in this case, our desired outcome or our desired output is Q sub H, because our desire is to add more heat to our home. So we're not worried so much about making the cold outdoors colder. We can look at this as an infinite sink or a source of heat, and that we're trying to increase the temperature of the indoors. So our coefficient of performance is Q sub H over the work in, which can also be written as Q sub H over QH minus QL. And if we do the math on that, we'll find that the coefficient of performance for a heat pump is equal to that of a refrigerator plus 1. Okay, so if we rearrange the terms and compare them to one another. So a heat pump is more efficient at heating a house than it is at cooling a house. And that is because you get some net heat input because of the work that you're putting into a system. Okay, so the Q sub L is always going to be a smaller value than a Q sub H. So all things equal, your heat pump is better at being a heat pump for heating your house than it is being a refrigerant for cooling your house. The difference comes in that, you know, most people notice their heating bill increases in the wintertime, which you would think, well, it's more effective, it shouldn't increase, right? Well, if you think about the temperature difference between your house and the outside in the wintertime versus your house on the outside in the summertime, that's where the difficulty lies. So, you know, even though it's 90 degrees outside, maybe that's only a 20-degree temperature difference between your thermostat and the outside. So there's less heat that needs to be removed from the inside. But in the winter, if it's, you know, 0 degrees outside and you're trying to maintain it at 70 degrees, that's a 70-degree temperature difference that you're trying to overcome. So that's why your heating bill goes up in the winter, even though your heat pump's better at being a heat pump than it is being a refrigerator. Okay, any questions on that? All right, so let's do another example, very similar to the first one, but then in this case, it's a heat pump instead of a refrigerator. So we have a home that's maintained at 20 degrees Celsius on a day when the outside air temperature is -2 Celsius. The house is estimated to lose heat at a rate of 80,000 kilojoules per hour. If the heat pump under these conditions has a COP of 2.5, determine the power consumed by the heat pump and the rate at which heat is absorbed from the cold outdoor air. Okay, so we have a heat loss from our house, but what does that tell us, and how do we use it, and how do we set this system up? And just don't look at this part right here. Okay, I just told you where to look. Okay, so if we're losing 80,000 kilojoules per hour from our home, that's how much our heat pump needs to replace, right? So we're losing heat to the outdoors at this rate. That's how much heat our heat pump needs to supply in order to maintain the temperature at 20 degrees Celsius. So that's like 72 degrees Fahrenheit, something like that. So we can assume that that Q out is equal to Q sub H. We know the coefficient of performance. We know Q sub H. In this case, we want to find how much work is required, or how much power is required, work dot, and what is the value of Q sub L. So how much heat do we need to draw from the ambient conditions outside in order to maintain the temperature? So what do we do in order to find that? Okay, so you're saying, what's the equation for a heat pump? Okay, so it's Q dot H over work dot in. So different from that of a refrigerator. So this is where, again, the confusion comes in and we have issues, is making sure that you're analyzing the correct system. So Q dot H over work dot in. We know COP and we know Q dot H, right? So we can solve for work dot in. Work dot in is equal to Q dot H over our COP for the heat pump. So we find that value to be equal to, so 80,000 kilojoules per hour divided by 2.5 is equal to 32,000 kilojoules per hour. And if we want to know in terms of kilowatts, we divide through by 3,600 seconds per hour, we get 8.9 kilowatts. So that's work dot in is 8.9 kilowatts. And then Q dot L, how do we find that one? So work dot in is equal to QH minus QL. And we want to find QL. So Q dot L is equal to Q dot H minus work dot in. So we get this 80,000 kilojoules per hour minus 32,000 kilojoules per hour is equal to 48 48,000 kilojoules per hour. Okay, so this brings up an interesting thought. So work dot in is 32,000, and our Q sub L is 48,000. So we're actually getting more heat from the outside environment than the heat we could have received if we just converted this using an electric resistance heater. So we're getting 48,000, whereas if we just plugged in one of those space heaters, baseboard heaters, whatever, those electric heaters, we just get 32,000. So even an electric heater that's 100% efficient is less effective or less cost effective than using a heat pump. So on your heat pumps, you may have like an emergency heat setting, which in a lot of cases is just like resistance heaters inside the ductwork, or sometimes there's a backup furnace. But if it's the resistance heaters, it's a lot more expensive to run your heat pump in emergency mode than it is to just run it as a normal heat pump. Okay, so emergency mode is for days where it's so cold outside that your heat pump can't keep up, and it needs to run a defrost cycle because the compressor's outside and it can get frozen. But if it runs the defrost cycle, it switches from being a heat pump to a refrigerator just for a moment to defrost everything, and then switches back. Because on a heat pump that can do both, the evaporator and the condenser switch roles. So one will get hot, one will get cold, and then that's how it defrosts itself. So if you ever have like ice building up on your heat pump and it's not defrosting itself, you can flip it to heat pump mode in heat terms, or vice versa, depending on what season it is. Same with your car. If your car is freezing up because you're running the air conditioner too much, you can switch it to being the heater for a while and it will thaw everything out, and then you can switch it back. So that's pretty interesting, right? That you can actually get more ambient heat from the outdoors just through this cycle by using the idea of compressing, expanding, evaporating a refrigerant in order to get a net heat input to your house that's greater than it would be if you were just using a resistance heater alone. Okay, so that's why we have heat pumps, instead of just everybody using baseboard heaters for everything. Okay, so the energy efficiency ratings is a common designator, and this is like a standardized, I don't know which four-letter designation for the society that authorizes those is, but that you'll see it sometimes like on your heat pump information, or sometimes your refrigerator or air conditioner will have it in the documentation, and it's slightly different from the Energy Star ratings, but it's based on this. So the energy efficiency rating is a measure of how well your heat pump can remove heat, or how well your refrigerant can remove heat from a cooled space, and it's in BTUs per 1 watt-hour of electricity. And there's a conversion between EER and coefficient of performance. So if you're given an EER, you could calculate your coefficient of performance using the manual. And these values are usually given or calculated at some range for your system. So maybe your coefficient of performance works well when there's only a 30-degree temperature difference between what you're trying to cool and what is between T sub H and T sub L. But if there's a greater temperature difference between T sub H and T sub L, your coefficient of performance decreases, that it becomes increasingly more difficult for a heat pump to get heat from the outside as the temperature of the outside gets colder. Or as you turn your thermostat up, the coefficient of performance decreases as well. So sometimes they'll give a range, and they'll say between these two particular ambient conditions, this is your coefficient of performance. And so when you're looking for a device to heat or cool or be a refrigerator, whatever it might be, you want to find something that's very energy efficient, that does a good job of converting heat or using the work to remove heat from a refrigerated space or add it to an already heated space. So that's in documentation. So generally, it increases with different types of working fluids or more expensive compressors, more efficient compressors. So the cost of whatever device initially will probably be higher the more efficient it is, because more engineering has gone into it to make it a better device. They use better materials, better refrigerants, better compressors. So you have to kind of figure out, is the cost savings in electricity worth it to buy a more efficient device, and considering repair costs and things like that too. Usually it's way better just to buy something that's more efficient, that you save much more money in the long run, especially as energy costs go up. Okay, so most of the heat pumps that we have in this part of the world are air source heat pumps. So this is probably a familiar sight. There's some compressor that's sitting outside your house, little box. That's your heat pump, works as an air conditioner and a heater. And so the COP will change seasonally. It will also change depending on whether or not it's a air conditioner or a heater. But there are some heat pumps, I don't know of anyone around here that does this, that are ground source heat pumps. So rather than using the air as the temperature source or the temperature sink, they then use the ground. So they pump water through the ground, which a certain number of feet below the surface, the ground temperature is just constant. It's like 58 degrees or something like that year round. So regardless of what temperature it is above ground, if it's -20 or 110, that a certain distance below the ground is the same temperature. So using the ground source for a heat pump, it's much more efficient, and also it's predictable because the temperature of your source or your sink doesn't change, whereas the air temperature will change significantly from day to day here in West Virginia. So it's an alternate idea and thought to do that. You can also, instead of using the ground, some people run pipes through, like if they live next to a pond or a lake, that they can run those pipes through a pond or a lake as well, because the temperature at the bottom of a lake is generally fairly consistent throughout the year as well. So it's cooler in the summer and warmer in the winter than the ambient air conditions. Yes?
So does that depend on geography, or is it basically worldwide?
No, I think for the most part worldwide, I think that the temperature a certain feet below the surface is pretty consistent. Now, in like the Arctic tundra, you may have to go a little bit deeper, but yeah, it's fairly consistent. The problem here in West Virginia is that we have so much rock and clay and other very, very difficult materials to drill and lay pipe through, that it's not really cost effective to try to have something like this installed. So unless you live next to a lake or have some other way of doing it, it's not really easy to do that. Or if you somehow like have a coal mine under you, you can just like tap into, I don't know. But yeah, they don't do it a lot here. This is a lot more common in places where it's easier to drill through the ground than it is here in West Virginia for a homeowner. And you also can do it, you can do it vertically, which is always more expensive to drill vertically, or you can go horizontally, but that also requires that you have more property if you're trying to lay these pipes out horizontally. So some issues with that. This is mostly just an FYI because I think it's cool. We looked into it, and it's just not feasible to do it where we live because we're built on top of a rock. So heat pumps and refrigerators operate the same, okay, but the desired output is different, so that's why the coefficient of performance changes, whether it's a heat pump or a refrigerator. And most heat pumps, especially around here, are reversible, so we can use them as an AC in the summer. And actually, it's funny because my grandmother she doesn't talk about turning on the air conditioner. She calls it the refrigerator, turn on the refrigerator, and she calls her refrigerator an icebox. So she's still going back. Okay, and then the coefficient of a heat pump will always be, coefficient of performance for a heat pump will always be greater than that of a refrigerator with the same components, so identical conditions. So thermal efficiency versus COP, again, heat engines are work-producing devices, so they have a thermal efficiency, whereas refrigerators and heat pumps or any other work-consuming devices that operate between temperature limits, we have to use the term coefficient of performance because it's not possible to obtain a thermal efficiency greater than 1, but with coefficient performance, it usually is greater than 1. If it's less than 1, it means you've done something terribly wrong in designing your system, because you would be better off just plugging in a resistance heater. So if your heat pump has a coefficient of performance less than 1, then you're, I don't know what's happening. So then a comparison of cycles, again, we can look at them. They all operate between high temperature and low temperature source, or high temperature and low temperature bodies. In the case of a heat pump, the source is the high temperature and the sink is a low temperature. But in the case of the heat pump and the refrigerator, we're doing the exact same thing. We're moving heat from a cold environment and adding it to a warm environment. But it just depends on whether or not we're trying to make a cold space colder or a warm space warmer, whether we consider something a heat pump or a refrigerator. Okay. So if we're trying to remove heat from the refrigerated space to make it colder, then it's a refrigerator. If we're trying to add heat to a warm space to make it warmer, then it's a heat pump. Okay, because the cycles can be exactly the same. It just depends on what your desire is. Your desired outcome is to remove heat or to add heat. And then the coefficient of performances for those are similar but different. So make sure that you understand the distinction between them, and always thinking of it in terms of your desired outcome over required input is the best way to know, so that you never have to memorize the equations. You can always just think, okay, what do I desire in a refrigerator? What do I desire in a heat pump? I want to make a cold space colder, hot space hotter. What do I have to put in to do that? The same goes for a heat engine as well. But the desired output then is workout. Okay, so Kelvin Planck statement, we talked about this last time, how it's impossible to convert 100% of heat back into a work output. So we looked at two examples. One would be, okay, if we remove the condenser and then we just continue the cycle through the pump. We found out that doesn't work because you can't pump steam and it's going to destroy all your devices. We also talked about how you can't just take Q sub L and add it to Q sub H, because that's reversing the flow of heat transfer to take something from a low temperature and add it to a high temperature. So with refrigerants and heat pumps, there is an equivalent statement called a Clausius Statement, that it's impossible to construct a device that operates and produces no net effect other than to transfer heat from a low temperature body to a high temperature body without having a work input. So essentially what this is saying is you can't reverse the flow of heat without using work. And these two are actually equivalent statements. So if we look at them together, let's just say for an example that we have a heat engine that violates the Kelvin Planck statement. So we have Q sub H being converted 100% into a network output. And then we use that to power a refrigerator. So if we have this network output going into our refrigerator, and then we have Q sub L that it's removing from the low temperature environment, and then it will be adding Q sub H plus Q sub L to this high temperature reservoir because we have that work input of Q sub H. So if we draw the system boundary around that, we have a QL in, a QH in, and then we have a QH plus QL out. So the equivalent system, if we condensed it down, would just be QL going from a low temperature reservoir to a high temperature reservoir. So violating the Kelvin Planck statement also violates the Clausius statement, and they're both equivalent in terms of the second law of thermodynamics, just that we can't create work 100% from heat, and we can't transfer heat to a higher temperature reservoir without adding work to it. Okay, so we have a couple more examples. We'll go through these somewhat quickly. But this one, read the problem and tell me what type of system it is. So again, we're identifying our system, making sure we understand it, and then how do we analyze it? Okay, so what is this device, or what is it? Okay, it's a heat pump, so we need to recognize that and understand it right away, that our desired outcome is what? For a heat pump. What's the desired outcome? QH, right? We're making a warm space warmer for a heat pump. Okay? And in this class, so I know heat pumps are reversible and they can be operated as air conditioners, but if we're talking about it as an air conditioner, we call it a refrigerator. So it's a heat pump, and we're trying to make a warm space warmer, so our desired outcome will be the Q dot H, and then our required input will be the work dot in. So if we calculate the coefficient of performance, we're going to need Q dot H and work dot in. But in this case, we're not given explicitly this Q dot H. What are we given? We're given the inlet and outlet conditions on a condenser. Okay, so this is a steady flow engineering devices. We're given a mass flow rate, we're given the inlet temperature and pressure, we're given the outlet pressure and quality. So we need to perform a steady flow engineering device analysis on the condenser in order to figure out what is Q dot H, right? Okay, so if we know the inlet conditions, we know the outlet conditions, we can do that. So the first thing that we need to do is perform an energy balance on the condenser. So we have Q dot in minus Q dot out plus work dot in minus work dot out is equal to M dot times H out minus H in, and then we're going to neglect kinetic and potential energies because we're not given any information about them. And they would probably be negligible anyway. Okay, so for this condenser, what interactions do we have? Do we have a Q dot in the condenser? Do we have a Q dot in for the condenser? No. Okay, so we're distinguishing between analyzing this system as a whole and just analyzing the condenser. Okay, so for the condenser, there's no Q dot H. So there's no Q dot in. Okay, do we have a Q dot out? Yes, that's Q dot H, right? Minus Q dot H. Do we have any work interactions on the condenser? No. Okay, so no work interactions on the condenser itself. The system as a whole, yes, there's work in, yes, there's Q in, but we're not looking at the entire system. We're just looking at the condenser. Okay, so you have to be careful about that. So we have a Q dot H and then M dot times H out minus H in. And in this case, we have our inlets and outlets labeled, so this would be H2 minus H1. So we can solve for Q dot H using steady flow analysis of an engineering device. Okay, so all that stuff we were doing in Chapter 5, we're still going to use it. Things are going to get a little bit more complicated than just when I give you Q dot H, right? Okay, so, but we can do this. So we have R134A, and the initial condition is 800 kilopascals and 35 degrees Celsius, so the inlet condition. What is the state of our fluid at that point? At 800 kilopascals, 35 Celsius. How would we figure that out? We have a pressure and a temperature. So pause in your mind this talk about heat pumps. And just go back to Chapter 5. How do we find the inlet conditions for a condenser? We know the fluid, right? What's the fluid? Yeah. Do we have anything that tells us about R134A? Tables, right? So let's go to the tables and see what is the inlet condition of this condenser. So at 800 kilopascals and 35 Celsius, what do we have? Make sure you're looking at R134A and not water. Okay, so the saturation temperature is 31.31, right? Are we above that? So then what is the condition? Superheated. Okay, so we need to go to table A13 and look up enthalpy at that point. Yeah, so 800 kilopascals and 35 Celsius, what is my enthalpy? So 800 kilopascals, 35 Celsius. Are you looking at the same table as is in the book or just one you found on the internet? Let me look. Okay, so 800 kilopascals Yep, you have to interpolate. Okay, so 271.18 is the value by interpolation. So that's from table A13. Okay, what about the outlet condition of the condenser? We're told X is 0 and at 800 kilopascals. Yep, so it's a saturated liquid at 800 kilopascals. H2 will be H sub F, which is yeah, 95.47, depending on which table you're looking at. This one says 95.48, so that's probably an older version, which is what my problem is based on too. So some of the stuff has changed slightly from addition to addition, but 95.47 or 48 kilojoules per kilogram. That's from table A12. Okay, so now we know enough information we can calculate Q sub H is equal to m dot, which is 0.018 kilograms per second, multiplied by H2 minus H1. I flipped those because I took away the negative sign, so H1 minus H2, 271.18 minus 95.47 kilojoules per kilogram. So we get Q dot H is equal to 3.163 kilojoules per second, or kilowatts. Okay, so now we want to determine the coefficient of performance, which for a heat pump is what? Yeah, so our desired outcome for a heat pump is to make a warm space warmer. So Q dot H over the work net in, work dot net in. So that's 3.163 divided by 1.2 kilowatts. So our coefficient of performance is 2.64. That's part A. Part B, the rate of heat absorption from the outside air. So which term is that? Heat absorption from the outside air on that diagram, QL, right? Okay, so how do we find QL? Just some more algebra. Q dot H minus Q dot L is equal to the work net in. So Q dot L is equal to Q dot minus, better look at my paper, Q dot H minus work net in. Right? Q dot H. Yeah. So Q dot L is equal to 3.163 minus 1.2 kilowatts. So Q dot L is 1.963 kilowatts. Okay, so this added an additional step, right? So rather than them just saying Q dot H is equal to whatever value, you say, okay, these are the inlet and outlet conditions on your condenser. Then you have to solve for Q dot H. They could do the same thing with the evaporator or with the compressor, you know, to find the work or the Q dot L. So being able to analyze, again, these steady flow engineering devices is important. Knowing how to use the property tables to look things up. Knowing how to determine if it's a superheated vapor, saturated liquid vapor mixture, using the quality sometimes to calculate, all of those things. Okay, so let's do one more example. So now, this time it's a refrigerator instead of a heat pump. So, you know, in practice, it's the same cycle, but in application, we're looking at different parts of it. So R134A enters the evaporator coils of a household refrigerator at 100 kilopascals with a quality of 20% and leaves at 100 kilopascals and negative 26 degrees C. The compressor consumes 600 watts of power and the COP is 1.2. So we need to find the mass flow rate of the refrigerant and the rate of heat rejected to the air. Okay, so this is a similar problem. What do we do to find the information that we need? Okay, so what do we want to analyze? The evaporator, right? So let's do our control volume is the evaporator itself. So what energy interactions do we have at the evaporator? Q in, right? Is there a Q out? Work in? No. Right. So only look at what's crossing the boundaries of your system. So if you've designed your system to be just the evaporator, or you have called it that with the imaginary boundary, you don't have to worry about the compressor and the condenser right now. You may have to analyze those later, but right now you just need to know what's happening with the evaporator. So this Q dot L we can solve for. So again, performing energy balance, Q dot in minus Q dot out plus work dot in minus work dot out is equal to M dot times H out minus H in. And in this case, we called H out is 2 and H in is 1. So however you want to design that. Okay, so real quick, we don't have a Q out, work in, or a work out. We only have a Q dot in is equal to M dot times H out minus H in. Okay, do we know M dot? No, we're trying to solve for that. Do we know a Q in? Do we have a value for that? Nope. What do we know about the system? Because we have two unknowns in this equation right now, so we can't solve for Q dot in until we know the mass flow rate. But maybe there's another equation we can use. Perfect. So COP of a refrigerator is Q dot L, so the desired outcome is to make a cold space colder, divided by work dot in. So we can solve for Q sub L is equal to this coefficient of performance multiplied by the work dot in, which is equal to 1.2 times 600 watts, which gives us 720 watts. Okay, so now we know Q in. We can solve for the mass flow rate, right? So mass flow rate is equal to Q dot in over H out minus H in, or in other words, Q dot L over H2 minus H1. So now we need to go to the property tables and look up some values to figure out our enthalpies. So at 100 kilopascals, X equals 0.2. So that's the inlet condition to the evaporator. We can look up property values and calculate using the H sub G and H sub F values that are H is equal to H sub F plus X HFG, and that value is 60.712 kilojoules per kilogram. Then at 100 kilopascals and negative 25 degrees Celsius, we can look up and find H by interpolation is 234.73 kilojoules per kilogram. So this is table A13 and this is table A12. So then if we plug in our values for that, we can solve for this M dot is equal to 0.720 kilojoules per second. So making sure that with watts, we convert it to kilowatts or kilojoules per second. And then divided by 234.73 minus 60.712, we get our mass flow rate is 0.00414 kilograms per second. Okay, and then part B, the rate of heat rejected to the kitchen air, Q dot H, is equal to this work dot in minus plus Q dot L. So we get that's 1320 watts. So you can see how with these heat pumps, refrigerators, and heat engines, there are 5 different possible control volumes that we could select. So the evaporator, the expansion valve, condenser, and the compressor individually, or we can look at the whole system as a whole. So although the problems are easier in a way when we're just looking simply at the system as a whole, we still need to rely on our information from Chapter 5 to analyze these steady flow engineering devices. So, any questions, just send me an email. Get started on the homework, make sure you understand it, and I'll see you on Thursday.